So, welcome back for another week of Mathematics 2. This week we're going to start a new chapter, and that is multivariable calculus. We'll start with an introduction, presenting the main features of this field, and then we'll go deeper. During this first week, we'll mainly recap results that we know from one-dimensional calculus over the real numbers. We'll deal with sequences, we'll deal with functions and continuity, and with limits. After that, we will introduce the concept of differentiation in higher dimensions. But let's start with the beginnings. So this is chapter 12. Multivariate calculus. And that first part is on fundamentals. So we'll start with part 12.1, Introduction. As you know, we've already dealt with functions that take multiple values as an input and also have multiple values as an output. Namely, we've talked about those in linear algebra. So you will remember in linear algebra we have functions of the form f that took an n-dimensional vector as an input and that outputted an m-dimensional vector. So you are already used to functions of that kind in a way. In the analysis part of our course Mathematics 1, however, we only dealt with one-dimensional functions. So our functions there were usually of the form r to r or some interval to r. And we investigated the properties of functions like this. Functions defined with one real input and one real output. Properties that we investigated included continuity, limits of those functions, differentiability, and then more advanced topics like approximation, optimization, and further on also integration. The aim of this chapter and the following ones is to generalize these concepts to higher dimensions. So, in general, we want to be able to accept multiple inputs, not just one real number, but multiple real numbers. And we also want to be able to deal with multiple outputs. So the output can also be a vector. So the general concept here is, from now on, we will deal with functions f that have a domain that will often denote by x and a codomain denoted by y, where x is a vector with n coordinates, so a subset of r to the n, and y is a vector with m coordinates, so a subset of r to the m. So these functions have two properties. The first one is they take multiple inputs, so that's why we call those multivariate or multivariable. And the other one is they give you multiple outputs. That's why they would be called vector valued. So that is the most general concept here. And of course, we also be dealing with simpler versions of these. For example, we look at functions that only take one real number as an input but produce a vector as an output. And we also look at functions that take multiple inputs but only produce a real number as an output. So before we go on, let's have a little definition, see what these functions are called, and see how their graph is defined, because of course we want to be able to visualize these if we can, of course, if the dimensions don't get too high. Okay, so here's the definition. Let f be a function from x to y and again, as in the one-dimensional case, x, the set x is going to be called the domain. X is a subset of R to the n. That's called the domain. And y a subset of R to the m, that's called the codomain. For mn in the natural numbers. And then we define the graph. Of that function. That's basically the same thing as in the one-dimensional case. That is just the set denoted by graph of f. The set consists of all points x in the domain and all corresponding function values f of x in the codomain. So we just use pairs x, f of x. The only difference to the real case being that now f and f of x may be vectors instead of just real numbers. Okay, so this is the graph. As a little shorthand, we usually write the input just separated by commas, and we'll do away with the extra vector bracket. So we write f of x1, x2, and so on to xn. Instead of, or be fully correct, f of the vector x1 to xn. And then we need double braces like this. And then one more special case. If the input consists just of a real number and the output is at least a two-dimensional vector, then we call that function a parameterized curve. The name will become clearer in a minute when we talk about visualizations. Okay, so if n equals 1 and m is at least 2, we call f a parameterized curve. So let's have a look at visualization on the question of how we can visualize these functions if the dimensions are not getting too high. There are a number of ways to do this, and we'll discuss those now. The first idea is if you have a function that takes as input two real numbers, so the domain is R2 or a subset of R2, and outputs just a real number, then the graph is still contained in R3, so we can draw that. So the graph of f is contained in R3. meaning we can just use the x1, x2 plane for the variables, and then the x3 axis for the function value. So we can directly draw the graph that results from that. And to give you an example of how that might look like, let's have a look at a possible graph. We'll use, we'll use the function f of x1, x2 is defined as x1 squared plus x2 squared as an example. So that's kind of the three-dimensional version of the classical parabola. So how does that look like if you visualize that graph? So what we have is first the coordinate plane with x2 and x3. Right, so this is, with x1 and x2. This is the x1 and the x2 axis. These are going to be the coordinates, the input coordinates, and then the output, we visualize that along the x3 axis, like this. So this is the x3 axis here. And that's going to be the output. Okay, so if you visualize this function, what we get is, first, of course, it contains the origin. And then as we move either along x1 or x2, the values increase quadratically. So we get a behavior that almost looks like the one in the one-dimensional real case. Just rotate it around. So basically, you have something that you can hopefully imagine how that looks like. Yeah, so that's a parabola rotated around the x3 axis. Okay, so that's how that graph looks like. That's one possible example. Of course, if dimensions get higher, then in theory this concept still holds, but we will not be able to draw that anymore because most we can draw is three-dimensional space. Okay, one other special case, one more example, is a function that takes as input the real numbers and as output, let's say, a vector in R2. R3 would also be possible. Okay, so this here is a curve, in this case, in the plane. And how can we visualize that? Well, the idea is to regard this input parameter as time and the output as the location. So we imagine that this function prescribes the location of some particle or whatever at a given time t. And what we can then do is visualize the movement of that particle through the plane as time progresses. Okay, so the idea is we regard input as time and the output as location, in this case in R2. So that means f of t is the location in the plane at time t. And what we can do is we can visualize the change of location, meaning basically the movement, as time progresses. Okay, so how could that look like? Let's say we're in the plane. So this is the two-dimensional plane here. And we want to visualize the movement of a particle. Let's say we start here. This is the location at time 0. And then the particle moves up a little, then down a little, then it takes a turn, and maybe it spirals a little, and then it ends up here. Yeah, so let's say this here, maybe this is time 2, and somewhere here in between there's time 1. And what you see is you can see the movement of the particle in space or in the plane, but you cannot exactly see which point corresponds to which time. So that information is somehow lost. Of course, you can mark certain time points along that line, but you have to explicitly do that to get that information. It's not immediately clear from the resulting graph. Okay, and technically speaking, this does not adhere to the definition of graph that we had before. So this is a curve in the plane. And of course, we can also draw curves in 3D space. So the location could also be a point in R3 instead of R2. Let's see one more example, because that's one that you will deal with more often in the future for such a curve, or maybe two more examples. First one I'm going to give you is we're going to look at a function that is defined on the interval from 0 to 2 pi and maps to a location in R2. And it's defined as f of t equals cosine t as a first coordinate and sine t as the second coordinate. Now, how does the graph of this function look like? Let's sketch that. Okay, so roughly, if time is 0, then the first coordinate is cosine of 0, that is 1. And the second coordinate is 0, so we are at this point here. So this is t equals 0. As time progresses, the second coordinate starts to grow, and the first coordinate starts to decrease, until we get to time pi over 2. At that time, the first coordinate is 0, while the second is 1. So this is our time point pi over 2. And in between, there's a movement somehow like this. Right? What happens next is the cosine, the first coordinate, goes into the negatives, while the sine, the second coordinate, starts to decrease again, until we get to this point here, and that corresponds to the time pi. And again, we get a movement somehow like this. And then you can imagine how that would continue. We cross this line here at time 3 pi over 2, and then we get back to the original point where we started. Yeah, so this here is the movement, that's the direction of movement here. So the curve here is exactly a circle of radius 1 around the origin. And of course we can have a look at a variation of that idea. So we'll have one more look at that. Basically, let's start with 0 to infinity to r this time. And f of 2 is now defined similarly, so we'll also have cosine t, sine t. So we have that circular motion, but at the same time we're going to scale these two coordinates by t. So that means we still have that circular motion around the origin, but the radius changes, starting at 0 and then growing and growing as time progresses. So what happens is roughly the following. We start at 0. So this is our time 0. And then we start doing the circular motion while at the same time increasing the radius linearly. So the resulting graph looks somewhat like this. What we get is a spiral around the origin. Okay? So that's a graph that works like this. And of course you can vary the degree at which the radius changes. So the spiral might grow larger, faster, or less fast, whatever you want to do here. Okay, so that's some possible ways of visualizing a function. There's one more way we should have a look at, and that's by using the level sets of a function. That's often useful if we work in higher dimensions, because it kind of cuts away a dimension from the visualization. So let's first define what a level set is. Let f be a function from x to r again, where x is a subset of r to the n. Be a function, and let gamma be a constant in R. Then the set, the following set, we'll define that as L f of gamma, the level set of f for the level gamma, that is defined as all x values, all x in capital X, where f assumes a value of gamma. So f of x equals gamma. That set is called the level set of f for level gamma. So basically we're looking for all x values that assume the same function value gamma. And with this definition, a function can also be visualized through its level sets. So as an example, again, consider the function that we had before, the quadratic function. F of x1, x2 is x1 squared plus x2 squared. You do remember how the graph of that one looked like. Let me just copy that here. So scroll back a little. That was that graph here. Let's copy this down here. And then the question is, what are the level sets of this function? So how do the sets where the level stays constant, how do these look like? To answer that question, we need to draw first the domain. So we need to consider the plane in this case. Okay, so this is the axis x1, this is the axis x2. And what do the level sets look like? Well, the level 0 is attained precisely at one point, namely at this here. So this corresponds to the level 0. If we go up and, for example, ask for the level 1, what x values is this level 1 attained, then you can see that we basically have to cut through that function here at exactly the value 1 here. And if we do that cut, well, what we get is basically a circle, right? So the level set corresponding to 1 is a circle. And of course, the same is true for every other constant value here. It's always a circle. And the circle grows bigger as we get higher and higher up in that function. Okay? So the level sets of this function, they just look like concentric circles around the origin. Imagine these were circles, actually, yeah? So these are the level sets of the function. And if you want, you can also write the corresponding level beside that. I'm not going to do that now. But of course, again, what gets lost in this visualization is the value of these levels, exactly, if you don't write them beside them. What you can see in this level set visualization is kind of the rate of change of the level. So if the level sets are closer together, then the change is faster. If they are further apart, then the change is slower. Okay, so that's what you can see here in this level set visualization. Okay, that concludes the introduction. We've seen how to work with multidimensional functions, how to visualize a few examples of those in the easy cases with not too high dimensions. Next, we'll introduce some basic notation, some basic concepts, and we also generalize concepts that we know from the reals to higher dimensions, like sequences, like limits, function limits, and continuity, before we then move on to differentiation. Thanks a lot.